An algorithm is a set of step-by-step instructions for solving a problem or completing a task. That definition is easy, so exam questions test the qualifiers instead, and there are three. An algorithm must be finite. It must end. An algorithm that loops forever has not solved anything. It must be unambiguous. Every instruction must have exactly one interpretation, which is why cook until done is not an algorithmic instruction, and heat to 180 degrees for 25 minutes is, and it must be effective. It must actually solve the problem it claims to. Everything an algorithm does fits the shape input, process, output. Data comes in, something is done to it, a result comes out. Hold on to that phrase because it comes back when we decompose a system into parts. Computational thinking has two ideas the syllabus names, and the first is abstraction, filtering out unnecessary detail and keeping only what is needed to solve the problem. The example on the page is the right one, a subway map. It shows stations and the lines connecting them. It does not show buildings, streets, distances, or even the true geography, because a passenger deciding which train to take needs none of that. And notice something important. The map is not a simplified map. It is a deliberately inaccurate one. The lines are straightened, the distances are wrong, and it is more useful because of it. That is what abstraction really is, not leaving things out to save effort, but leaving things out because they would get in the way. The judgment is in deciding what is unnecessary, and that judgment depends entirely on the problem you are solving. A map for an engineer repairing the tunnels would keep exactly the details the passenger's map throws away. The second is decomposition, breaking a complex problem into smaller sub-problems, each easier to solve on its own. The page uses making a cake, buying ingredients, mixing, baking. And the reason this matters is not that small problems are easier in the abstract. It is that small problems can be solved independently, tested independently, and given to different people, which is exactly what the structure diagrams lesson develops. Now, decomposition has a natural stopping point, and it is worth knowing. You stop breaking a subproblem down when it is simple enough to be solved directly, when you could sit down and write it as one straightforward piece of code. Going further than that produces a diagram with more boxes and no more clarity. Let me apply both to a single problem because that is what an exam question actually asks, and students can define the two terms and still stall. The problem, a system for a school library to manage borrowing. Start with abstraction. What matters? Which books exist? Who the members are? What is currently on loan and when it is due back? What does not matter? The color of the cover, the weight of the book, what the member had for lunch, the shelf's exact position in millimeters. That was abstraction, and note that I could only decide what was irrelevant because I knew the problem was managing borrowing. Now decomposition. That system breaks into subsystems. Search for a book, issue a loan, accept a return, calculate a fine, manage members. And each of those breaks down further. Issue a loan becomes check, the member is valid, check the book is available, record the loan, set the due date. Keep going until each box is something you could write directly. Notice the order in which I did those two. Abstraction first, deciding what the problem contains. Decomposition second, breaking what remains into parts. Doing it the other way round means decomposing detail you should have discarded. All of that sits inside a larger structure, the program development lifecycle, and each stage depends on the one before it. Analysis, understanding the problem. Its outcome is a requirement specification stating what the inputs, processes, and outputs must be. And that document matters later because the finished program is eventually tested against it. Design, planning how the software will work before writing any of it, which is where structure diagrams, flowcharts, and pseudocode belong. Coding, writing the program in a programming language and correcting errors as you go. Testing, checking it works, both during development and once complete. And maintenance, fixing faults found in use and making changes as requirements change. The stage students underrate is analysis, and the reason is worth stating. A misunderstanding at that stage survives every later stage untouched. You can design, code, and test perfectly and deliver exactly the wrong program. Testing happens at two scales and the syllabus names both. Iterative testing is done during development. Each module is tested as it is written, corrected, and retested repeatedly, which is what iterative means. The point is to catch a fault while the code that caused it is small and you still remember writing it. Final testing is done after development, when all the modules are combined. The complete program is tested against the original requirement specification from the analysis stage, and both are necessary for a reason worth understanding. Iterative testing checks that each part works. Final testing checks that the parts work together and that the finished program does what was actually asked for. A program can be made entirely of modules that each pass their own tests and still fail as a whole, because modules pass data between them and nobody tested the joins. Which is also why final testing refers back to the requirements rather than to the code. Iterative testing asks, does this module do what I intended? And final testing asks, does this program do what the customer asked for? 4 things to take into the exam. First, define abstraction as removing unnecessary detail and keeping what is needed to solve the problem. And if you give an example, say what was removed and why it did not matter. Second, define decomposition as breaking a problem into smaller subproblems, and be ready to actually do it for a described system rather than only defining it. Third, name the lifecycle stages in order: analysis, design, coding, testing, maintenance, and know what each produces, particularly that analysis produces the requirement specification. And fourth, distinguish iterative testing during development from final testing against the requirements once the program is complete. Those 2 terms are examinable, and they are the ones most often missing from an answer about testing.